Hi everyone, this is Mrs. GA, and today we're going to be graphing rational functions. So for each of the following functions, together we are going to list all of the intercepts. We're going to define all asymptotes or holes of your graph. We're going to define the end behavior of our function. We're going to define behavior around the asymptotes, which is a new thing we'll talk about today, and then we're going to sketch a graph. All right, let's start with this first one together. So I'm going to start by factoring our function, just because I know we're going to need to do that eventually. So in my numerator, I have 2 times x plus 3. And in my denominator, I'll factor out negative 3, which leaves us with 2x minus 1. Okay, from here, we can start by finding the x-intercept. So remember, we find the x-intercept by essentially setting our numerator equal to 0 and solving. So we get an x-intercept at negative 3, 0. So again, if I set my numerator equal to 0 and I solve, I get negative 3. For y-intercept, remember we find this by replacing all of our x values with 0, leaving us with 6 over 3, which is 2. So our y-intercept is at 0, 2. Now let's move on to the vertical asymptote. So here I can see that I have a restriction at x equals 1/2, so that will be my vertical asymptote. And remember, for a horizontal asymptote, we compare the degree of the numerator and denominator. In this case, I see that the degree is the same, so our horizontal asymptote will always occur at the ratio of the lead coefficients. So here we have 2 over negative 6, which is y equals negative 1/3. So let's try sketching this graph before we describe the end behavior and asymptote behavior. So again, this is just a really rough sketch. So my first asymptote is going to be here at x equals 1/2. My horizontal asymptote, we'll say, is right here. We'll just label it y equals negative 1/3. My y-intercept is at 0, 2, so somewhere around here. My x-intercept is at negative 3, 0. So I do have a graph that looks something like this, which means the other portion will be in this quadrant. So now we can describe the end behavior of our graph. So this is going to be a little bit different than the end behavior of polynomials, because now we have horizontal asymptotes. So let's start with as x approaches positive infinity. So I can see here, as x approaches positive infinity, my line is getting closer and closer to this asymptote, which is at negative 1/3. So f of x equals negative 1/3. And same as x approaches negative infinity, you can trace your graph and you can see that it's approaching our asymptote. So f of x equals negative 1/3 as well. So asymptote behavior is a little new. So it's essentially describing what is happening to our graph as we approach any vertical asymptote from the left and the right. So first, let's talk about notation. I'm going to start by writing this as x approaches 1/2. That's where my asymptote is. And then I'm going to put a little minus sign right here, which means from the left. So if I trace it, as I'm approaching from the left, I see that my graph is going up forever. So I say f of x approaches positive infinity. And then here, as x approaches 1/2 from the right, I can see that my graph is going towards negative infinity. So that would be our asymptote behavior. All right, let's try this next one together. So again, I'm going to start by factoring this out. Okay, so I see that I don't have any removable discontinuities, so now I can start listing all my information. So the x-intercept in this case, if I set my numerator equal to 0, I get an x-intercept at negative 2, 0. For the y-intercept, again, substitute x with 0 and I get 2/3, so 0, 2/3. For your vertical asymptote, again, it's going to be your restriction. So in this case, we actually have 2. One at x equals negative 3 and one at x equals negative 1. For your horizontal asymptote, let's compare the numerator and denominator. So I see that the degree on the bottom is larger than the degree in the numerator. So that means my horizontal asymptote will be at y equals 0. All right, so here let's sketch a graph before we describe our end behavior. So let's call this x equals -3 and x equals -1, and an asymptote at y equals 0. Okay, so now we're going to start trying to graph our function. So here we are going to need to be plugging in points to figure out exactly where our graph is, but we can start with the points we know, which would be the x-intercept at -2, 0. So we'll say that's right here. And our y-intercept at 0, 2/3. Okay, so this y-intercept does imply that we will have a section of our graph that looks like this. But when we look at this middle part, we need to be careful. Notice that this point is actually on our horizontal asymptote. So for horizontal asymptotes, they don't act like vertical asymptotes in the fact that you can never, ever, ever cross them. Horizontal asymptotes are more of a limit. It's what your graph will approach as x approaches positive or negative infinity. So you'll typically see when you have a case where you have two vertical asymptotes, it's very common for your graph to actually cross over your horizontal asymptote somewhere in between. So with these, we also need to be careful because we might end up with a graph that looks like this, or maybe we'll end up with something that looks like this. So sometimes you're going to have more of a parabola shape, or sometimes you're going to have more of this cubic shape. So I think a good place to start would be on the far left region, and then we'll fill in the middle part at the end. So again, let's see what we can figure out about this side. And really all we need to do to find what's going on this side is to plug in a single point that's left of -3. So maybe let's find what f of -4 is. So if you substitute f of -4 into our function, we end up with -2/3. So I know that that would be somewhere around here, which tells me that my graph is going to be in this portion of this section. So it's going to be on the bottom half and not the top half. So typically speaking, around our vertical asymptotes, we're always going to have opposite end behavior. So if I see that it's going down over here, that means that it's going to go up on this side. And since I see that's going up on this side, it's going to go down on this side. So I do end up with this kind of cubic shape like this. However, the best way to be sure of this is to simply test a point that's slightly to the right of -3. Just plug it into your function and then test a point that's slightly to the left of -1. So for example, we could find f of -2.9. And then we could find f of -1.1 and see what we get. So f of -2.9 is 4.7, so that implies that our graph is going to start going up as x approaches -3 from the right, and f of -1.1 is -4.74, so that implies that it's going to go down on this side. So now that I have my graph, I can start describing the end behavior. So let's start with as x approaches positive infinity, I can see that f of x approaches 0. So as I move to the right, our graph approaches y equals 0. And it's going to be the same on the left. As x approaches -infinity, f of x approaches 0. Let's do our asymptote behavior. So as x approaches -3 from the left, f of x approaches -infinity. So that's describing this portion. As x approaches -3 from the right, f of x approaches positive infinity. as x approaches -1 from the left, f of x approaches negative infinity. So that's describing right here. Now let's describe as x approaches -1 from the right. We can see that our graph is going up, so f of x approaches positive infinity. Okay, let's try this next one together. So here we have x squared plus 3x over x squared plus x minus 6. So of course I'm going to start by factoring. So x times x plus 3 all over x plus 3 times x minus 2. So you notice here that we have one of those removable discontinuities. So remember, in terms of our graph, this removable discontinuity is going to create a hole. So the way, well, we know that the hole is going to occur at x equals -3, but we need to know the exact coordinate of that hole. So I'm going to take -3 and I'm actually going to substitute it in here. Of course, if I substitute it into my original equation, I get something that's undefined. So we're going to substitute -3 into our reduced simplified function. So we have -3 over -3 minus 2. So f of -3 is positive 3/5. So we know we have a hole at -3 3/5. Let's take a moment and describe the rest of our asymptotes. So I can see that I have a vertical asymptote at x equals 2 because of the restriction in my denominator. And then since the degree of my numerator and denominator are the same, I'm going to look at their lead coefficients. So I see that I have lead coefficients of 1 over 1, so that's where my horizontal asymptote will be, at y equals 1. Before we start graphing, we should list out our intercepts as well. So looking right here, I can see that I have a x-intercept at 0, 0. And we know that that will also be where our y-intercept is. Okay, so now we're ready to start sketching a graph. Okay, so let's say that this is at x equals 2. Label it down here. And then let's sketch in our horizontal asymptote at y equals 1. Notice this is a super rough sketch, not drawn to scale at all, but as long as I label it, at least we can tell what's going on for our particular graph. The one point that we know so far is 0, 0, and we know a point that has a hole at -3 3/5. So let's say that that's somewhere right around here. So that implies that I'm going to have a graph that looks like this. So notice that it really just continues on with the curve and it goes right through the hole. So just make sure to include the hole in your graph, and then the rest is just like a normal rational function. And then we'll have the other portion in this opposite quadrant. Of course, we can test this by plugging in some additional points. So let's make sure that our graph is actually falling in that quadrant. So let's test, I don't know, f of 3 and see what we get. So you should get that f of 3 is 3, which confirms that we do have our graph up in this quadrant. Okay, so now we can describe end behavior and asymptote behavior. So I can see that as x approaches positive infinity, my graph is approaching my horizontal asymptote, so f of x approaches 1. As x approaches negative infinity, f of x approaches 1, the horizontal asymptote. As x approaches 2 from the left, f of x is going down right here, so f of x approaches negative infinity, and as x approaches 2 from the right, my graph is going up, so f of x approaches positive infinity. Okay, let's give this next one a try together as well. So here we have x squared plus 2x over x minus 1. So let's factor out our numerator just to confirm that we don't have any removable discontinuities or anything like that. So now let's start by listing our x and y intercepts. So I see that I have two x-intercepts here. I'm going to have an x-intercept at the origin and at -2, 0. I know that my y-intercept is at the origin. I can see that I have a vertical asymptote at x equals 1. And then here, since the degree in the numerator is larger than the degree in the denominator, I know that I don't have a horizontal asymptote. But since the degree in the numerator is exactly 1 more than the degree in the denominator, that does mean that I am going to have a slant asymptote. So remember, the way we find the equation of our slant asymptote is by doing a little bit of long division. So here I have x, leaving me with x squared minus x, and I'm going to subtract. So I get 3x, bring down the 0, and then here I have 3, so 3x minus 3. And remember, as soon as we reach the point where we can no longer divide, this is going to be the equation of our slant asymptote. So we have a slant asymptote with the equation y equals x plus 3. So let's see if we can sketch a graph of this. So this one, just to show a little more about the slant asymptote, I'm going to make it a little bit more accurate. So again, we have our vertical asymptote at x equals 1. And remember, this is just a linear equation that has a y-intercept at 0, 3 and a slope of 1 over 1. So I'm going to have something that looks like this. Okay, so I know that it looks a little bit funky, but our graph is going to fit into 2 of these quadrants, and it is going to run along the slant asymptote. So I'm either going to have a graph that goes like this and like this, or like this and like this. So using the points we know, well, I know that my x and y-intercept is at the origin, and that I have another x-intercept at -2, 0. So this actually implies I'm going to have a graph that looks kind of like this. So it's going to go like this, and then it's going to turn around and go back down this way. So remember, your graph cannot cross at any other points than here and here. So this is really the only way to make this work. And then that implies that the rest of my graph is going to be opposite of it up here. So it's going to run along like this. So a little bit different than we're used to, but if you list out everything you know about your function from the beginning, it makes it much easier to piece everything together. So now let's talk about end behavior. So this one, as x approaches positive infinity. Well, let's look at what our graph is doing. So as x is getting increasingly big, I have a graph that is following around this asymptote, and it is heading up. So this end behavior does approach positive infinity. And then as x approaches negative infinity, again, let's look at our graph. As I'm getting larger, going to the left, I see that I'm following this asymptote but going down. So this side is going to approach negative infinity. And then for asymptote behavior, as x approaches 1 from the left, so I'm going to describe what's going on here. I see that f of x approaches negative infinity, and as x approaches 1 from the right, I can see that f of x approaches positive infinity. So we can infer that whenever we have a slant asymptote, we're going to have end behavior that looks more like a polynomial function, where it's going to approach positive or negative infinity. But it will follow the slope of this slant asymptote. Okay, so we're going to try one last example together. So here we have f of x equals x squared plus 3x over x squared plus 2x minus 15. So let's start by factoring this out. So we have x times x plus 3 over x plus 5 times x minus 3. Okay, so let's start with our, how about x-intercepts? So here I know that I have an x-intercept at 0, 0, and negative 3, 0. Again, we get that by setting our numerator equal to 0. For y-intercept, it's going to be at the origin. I can see that I have two vertical asymptotes and no holes. So I have one at x equals negative 5 and one at x equals 3. For my horizontal asymptote, since the degree of the numerator and the denominator are the same, I use the lead coefficients for my horizontal asymptote. So at y equals 1. So now we have enough information to start sketching our graph. So here's, let's call this x equals negative 5. And here's x equals 3. And then y equals 1. So I want to remind you that when we have two vertical asymptotes, it's perfectly acceptable for our graph to cross over our horizontal asymptote somewhere in the middle here. Again, a horizontal asymptote is more of a long-term limit. It does not act like a vertical asymptote where our graph never ever touches it. But we don't really know if we have a graph that looks something like this, a graph maybe that looks like this, or maybe a graph that looks like this or this. So we're not sure if we're going to have more of a parabola shape or more of a cubic shape. So the only way to figure out is to start finding points that we know. So we are going to start with the x-intercept. So I have one here at 0, 0, and then I have one here at negative 3, 0. So it's slightly to the right of our asymptote. So if I'm looking here, and I'm wondering, well, okay, how can I make these two touch? It's either going to be with something like this or with something like this. Those are the only two ways that we can make this work. So this one is going to have more of a parabola shape in the middle rather than that cubic shape. So before we figure out which way this goes, let's see if we can figure out what's happening on the outer bounds. So to do that, again, we'll plug in a point, some point to the left of negative 5. So let's plug in let's find f of negative 6, and then somewhere to the right of this asymptote. So we'll find f of 4. You're going to plug them into your function. Okay, so you should get that f of negative 6 is 2, so it's going to be somewhere in this area, and then f of 4 is 3.1, so it's going to be somewhere in this area. So that means I'm going to have a graph that looks like this, and then another portion that looks like this. So since I have these end behaviors, I can probably guess that my end behavior is going to be opposite on the other side of my asymptote. So I'm predicting that I have something that looks like this. But of course, the only way to be absolutely sure is to maybe plug in a couple more points. So let's see if we can find f of negative 4.9. So that's a point that's directly to the right of our asymptote. And then let's see if we can find f of 2.9, which is directly to the left, just to make sure that this type of behavior is correct. Okay, so hopefully you got that f of negative 4.9 is negative 11.78, which does suggest that our graph is going to go down as it approaches this asymptote from the right. and f of 2.9 is negative 21.66, which again suggests that our graph is going to go down as we approach this asymptote from the left. So now that we have our graph, we can start describing end behavior and asymptote behavior. So as x approaches positive infinity, our graph approaches the asymptote, so 1. As x approaches negative infinity, our graph approaches the asymptote again. As x approaches negative 5 from the left, we can see that our graph is going up, so positive infinity. As x approaches negative 5 from the right, f of x approaches negative infinity, so our graph is going down. As x approaches 3 from the left, our graph goes down, so f of x approaches negative infinity. And as x approaches 3 from the right, f of x approaches positive infinity. And there you have it. All right, that is all for today's video. Thank you so much for watching.